Hi, my name is Jack Gettys, and I'll be presenting to you today a brief comprehensive analysis on steam traps. Steam is a widespread energy source in the complex industrial world. At the core of steam systems exists an unassuming yet vital component, the steam trap. Its main purpose is to discharge condensate, air, and other incandescible gases without letting steam escape. The earliest documentation of steam utilization was seen by Heron's A. Lapile, as seen in the figure to the right, which is a steam turbine featuring a freely rotating hollow sphere and two curved pipes for steam release. It wasn't until the 18th century that the potential of steam was realized to be a prominent heating source, and steam traps were invented to help release condensate. As stated before, steam traps play a crucial role in managing steam and condensate, ensuring optimal heat utilization, which can be affected by the presence of unwanted substances. The basic functionality of a steam trap can be seen to the right. When steam enters, the product inside the jacketed kettle is heated. When steam does its work, it condenses and becomes condensate. The heat transfer surface area grows smaller as the condensate builds up, so the condensate must be removed. Removing the condensate by merely opening normal valve will discharge the condensate, but steam may also be discharged, which we don't want. A steam trap will discharge only condensate, while preventing any leakage of steam. To properly sense the different variables in entering fluids, there are three basic operating principles or designs of steam traps, being thermostatic, density, and thermodynamic. These three sense the differences in temperature, density, and velocity of entering fluids. Steam traps can be seen in a wide range of industries such as power generation, chemical manufacturing, food processing, and HVAC. They are crucial in maintaining optimal energy use and preventing equipment damage. They are strategically placed in systems and equipment like heating systems, food processing, and dry cleaning equipment to remove condensate and manage the steam in them. They are most commonly used in drip applications though, which involves condensate forming in steam lines when the steam has lost its heat energy. Density traps, also known as mechanical traps, are designed to sense the density difference of entering fluids by opening and closing the valve using the buoyancy property of a floating object. Mechanical traps have two distinct categories that apply to the density principle: float and bucket. Each of these has their own two types of traps, which are lever float, free float, inverted bucket, and open bucket. Figure 3 portrays how inverted buckets contain an inverted, cylindrically shaped bucket which is open on the bottom side, where condensate, the purple area, flows. The inverted buckets gain buoyancy by closing the valve when steam or air, the red area, enters the inner chamber. Levering the bucket weight and cantilevering off the valve block can be done to open them. Thermodynamic traps, also called disc, piston, or impulse traps, sense the velocity difference of entering fluids. There are two basic categories of thermodynamic traps that work on the velocity principle: thermodynamic disc and thermodynamic piston. Figure 4 details the process of a thermodynamic trap below, where it involves cool, purple area, medium temperature, burgundy, and hot, red area, condensate. When water from condensation enters the trap, it moves slowly compared to steam and is released freely. When fast-moving flash or live steam passes under the disc, its high speed causes a pressure drop, closing the valve. The valve remains closed until the pressure of the steam in the control chamber above it decreases, allowing the valve to open again. Thermostatic traps operate by detecting temperature variations in incoming fluids. They are designed to open for cooler condensate or air and close for hotter condensate. Closure happens when the fluid, usually hot condensate, reaches or exceeds a specific temperature. There are three main types: expansion, balance pressure, and bimetal. Expansion traps, as seen in Figure 5, use an internal filling that expands or contracts with temperature changes, with two basic designs: wax or petroleum-based liquid. Condensate is seen as both cold and hot in the figure as purple and burgundy. An oil-filled, cool yellow and heated orange element expands when heated to close the valve against the seat. Proper maintenance is essential in ensuring the efficient and reliable operation of steam-based systems. Regular inspections help identify and address issues such as steam leaks, malfunctioning valves, or blocked passages that may compromise the performance of the steam trap. The impact of malfunctioning steam traps can be significant, leading to increased energy consumption, decreased system efficiency, and potential damage to downstream equipment. It can be seen in Figure 6 that water hammer occurs when a valve is closed quickly or a pump shuts down and causes the water pressures to rise and fall rapidly. This will sound like hammering on a pipe and cause them to burst. The key method for preventing water hammer is to eliminate water from the steam lines before reintroducing steam into them. It can also be seen in Figure 7 how engineers can slope steam pipes in the direction of flow to ensure a steady and controlled flow of condensate. This video will help explain how important proper maintenance is and how dangerous water hammer can be in a steam line without the application of steam traps.
Imagine this. You open a valve allowing steam to flow into a steel pipe. As the steam comes into contact with that cold steel, it condenses. The problem is that steam takes up about 1,600 times more volume than its equivalent mass as a liquid. So when it condenses, it literally shrinks. In a closed container like a pipe or this glass bottle that just came out of my microwave, that collapsing steam can lead to catastrophic damage. Water rushes to fill the vacuum created by condensation, cooling the steam even further and creating a runaway situation. This can happen extremely fast, and all that water can accelerate and decelerate violently, hence the name steam hammer. If it's violent enough, it can rupture the pipe, leading to an explosion like the one that happened in New York City in 2007. Condensation in a steam pipe is always occurring just from normal transfer of heat to the outside air. And this is roughly what that might look like. I'm using compressed air here in lieu of steam for the obvious safety implications. Engineers manage this condensate by sloping steam pipes and by installing devices that can get rid of condensate from the pipes called steam traps. Steam traps are a fascinating topic on their own, but occasionally they get clogged or malfunction, allowing condensate to build up. When water and steam flow together in the same pipe, it's known as biphase flow. In this situation, the velocity of the steam is usually much higher than the velocity of the flowing liquid water. If there's only a little bit of condensate in the pipe, that's not really a big deal. But if condensate is accidentally allowed to pool up, things can get dangerous. The steam passing over the top of the liquid can create turbulence and waves. If those waves get high enough, the liquid can create a complete seal inside the pipe with the full pressure of the steam behind it. This seal of water becomes a slug or piston and accelerates down the pipe like the barrel of a cannon, picking up more condensate as it travels. This slug of liquid eventually slams into the end of the pipe, resulting in a dangerous pressure spike known as differential shock.
Here is a quick overview of the important topics we discussed. Steam traps are designed to discharge condensate and any other incondensable gases without letting steam escape. There are three basic designs of steam traps, which are chosen specifically based on sensing different variables in entering fluids. Steam traps are used in a variety of applications in the industrial world, most commonly in drip applications. And without the proper maintenance and routine checks, efficiency can decrease tremendously, or worse, have a dangerous event occur due to water hammer. Here are all my references, and this is the quiz. I hope you all enjoyed this presentation on steam traps. Thank you.